Okay, let's start our final for the day. So I'm given the three more papers in the system. And without further beginning, I'd like to speak Hamid Bostani. So Hamid going to talk to improving adversarial robustness and going malware protection by reducing the impact of spurious foreign corporations. Hamid is over to you. That's what this my it's working now. Okay.
Technical.
Good afternoon, everyone. First of all, I thank you for all being here. I also want to thank the organizer because of giving me the opportunity for presenting my work here. My name is Hamid Bostani. I'm a PhD candidate in the Digital Security Group of Adversarial University. My research area is security of machine learning, particularly the malware domain. And today I'm going to talk about one of my research studies titled Improving Adversarial and value detection by understanding of service relations. This is a joint work with Zhengyu, Zhao, and Veelasha. Okay, let's get started. I think that everybody here might come across with some breaking news about malware. Malware is any malicious software that aims to compromise the computer systems, such as laptops or smartphones. But one of the malware can come with different forms. One of the dangerous forms of malware is the Android malware. And during the last years, both academia and industry hardly worked to propose some technique to protect Android devices from malware. And one of the interesting approach is utilizing machine learning for malware detection. And the pipeline of for malware detection, we need, based on the machine learning, we need to build a classifier, and the pipeline of the malware detection for using machine learning for malware detection is similar to the our pipeline. In the training phase, we need to build a malware classifier. In our case, malware classifier is the predictive is the binary classifier. In the inference phase, we can use the malware classifier for classifying unseen sample or unseen in our case or unseen sample is and Julia. And this pipeline or actually the malware classifier suffers from some attacks. For instance, in the web, we might have some malicious actors that aim to bypass the malware classifier by manipulating the Android and the malware app in a way that the manipulated app not only bypass the malware classifier, but also can compromise the victim machine. We call this sort of malware as the evasion attack. And what can be generated by the adversarial or malicious actor is the adversarial examples. And what maybe one of the questions is why malware classifiers are vulnerable against evasion attack. And here I try to explain why. One of the maybe problem goes back to the generalizability issue, which is a common problem of in the machine learning domain. For instance, suppose we have the red and the green samples show the representation of the malware and rootware apps in the feature space, and we use a machine learning technique such as NLP or SPM to build the classifier. and or malware classifier during the training phase or after the training phase, or malware classifier will be learn the white line. This is the decision bounding that can be learned by the malware classifier based on this data. But the problem is our classifier cannot classify the blue sample correctly, because as you can see here, the optimal decision bounding, these blue samples are indeed malware, not a good hack, because our optimal decision bounding classify these samples as a malware. So it goes back to the generalizability issue. And the classifier, so it means that the classifier cannot classify that some samples that are placed in the region between or learn decision bounding and the optimal decision bounding. And it can be misused, this region, it can be misused by the adversarial attack. It means that if the adversarial attack moves the malware sample to inside this area, so the classifier malware classifier cannot classify the sample or sample correctly. And one of the key reasons for that led to poor generalizability is the spurious correlations. Spurious correlations actually are some sort of correlations that relate between the features in the feature space and the target name. And this correlation is not related to our desired task. Our desired task here is detecting or identifying the malicious patterns. And this, as I said, that the spurious correlation can lead to poor generalizability, and there are different reasons for that causes spurious correlations. For instance, if you use a biased data set, you might your machine learning model can be learned the spurious correlation. For example, here I try to show an example. As you can see here, we can assume that we want to collect some apps from Google Play Store and Amazon App Store, and these apps will be our training data set. And the problem is here is as you can see here, the majority of the malware apps collected from the Amazon App Store, and then you use this biased data set to build another classifier. The classifier might have learned some spurious correlation. For example, in this case, the classifier will be learned market as one of the most influential features that is important for classification. So actually, it means that the classifier would be rely on market information to make a decision about the samples, and it will cause the false positive very high false positive rate in some cases. For instance, if you use a good word from the Amazon App Store, your classifier cannot classify the samples correctly. And spurious correlation are interesting for realistic evasion attacks because they have a significant influence on the classification of outcomes, and also they don't affect malicious functionality of the apps because they are not related to the genuine correlation. For instance, if you remember, I've mentioned that one of the goal of the adversarial attack is making sure that the manipulated app can compromise the victim machine. So it's important to attackers to make sure that the malicious functionality can be preserved after applying the adversarial perturbation. So the features contributed to spurious correlation are good candidate for the realistic evasion attack. And here I provide an example. And as you can see, this example is based on what I mentioned in the previous slide. For instance, in this example, an attacker can inject an snippet of code that causes Google Play information to appear in the apps. And this manipulation can fool some classifiers that rely on the app markets for classification. There are different techniques in the literature that aims to address the spurious correlation. One of the maybe successful technique is the domain adaptation. And the idea in the domain adaptation is adjusting the making the distribution, aligning the distribution of the source domain and the target domain. For instance, in the malware domain, for training apps is the source domain, and the unseen apps is the target domain. One of the types of unseen apps is the adversarial malware. And as we can see here, we can show when we represent these apps in the feature space, maybe the distribution of the source domain and the target domain can be different. So the idea is we can use some techniques to aligning the distribution of the for training apps and unseen apps in the feature space. And if we can do it, it help us to build a robust. But you might ask me that why? The reason is when the robust model aims to learn robust features. And then you model learn the robust features, then the adversary cannot fool the malware classifier easily, because changing the robust feature is not easy. For instance, robust features shows the semantic patterns in the feature space. Actually, here I provided an example from the computer vision. For instance, suppose we want to make or build an image classifier that aims to classify the images of animals. And in this case, we want to classify the images of the frog correctly. And the semantic patterns in the images, input images, are something related to the frog. And if the model learns these patterns, then this means that the model can learn the robust feature, and the results, I mean that the trained model will be robust against adversarial attack, because if an adversary cannot change these robust features, because if it changes this robust feature, it means that they can break or destroy the images. And so it's important to for adversary to generate some adversarial example in the computer vision that is imperceptible from the human observation. In the future, in the disparate domains such as malware domain, the feature dependencies can show the semantic patterns. For instance, here I show some features. Suppose you can assume that feature F1 and F8 characterize the dimension of the features space in the malware domain. And as you can see, there are some dependencies between features. For instance, the dependency between F1, F3, and F7 can show, can specify the features that contributed to specific, functionalities such as sending an SMS. Okay, so the ideal, we propose an ideal based on the domain adaptation. And actually, specifically, we propose a robust feature space. And the idea is after representing the apps in the initial feature space, we need a transformation, a feature transformation to transform the representation of the apps in the feature space to another feature space that is called, that we call robust feature space. And this transformation would be done based on the feature dependencies, because the feature dependency shows the semantic of the apps. So and if the classifier will learn from the samples in the robust feature space, it means that classifier can learn robust feature, and also the distribution of the or apps, I mean the malware apps or adversarial maps are closed. And let's take a quick look at our feature transformation. And as you can see here, we have an initial feature space named capital X, and our robust features is shown by the capital H. And the idea or the intuition is we must transform each feature vector such as X, which is a representation of the apps in the initial feature space, to another feature vector in H. But for doing it, we first need to identify the feature dependencies. We use a graph-based pattern recognition technique to find the dependencies between features. This technique partitions the dependent features to the same cluster. So for each cluster, we have some dependent features. And moreover, in robust feature space, we will have a feature that is that corresponds to each cluster. And in next step, for each sample, we must transform the influence of the features in each cluster to H. We propose an activation function, and the idea is aggregating the values of the features in each cluster based on the importance of the feature and after that we use a segment function, and based on the segment function and the threshold, we decide that whether a feature should be appears in the new feature vector or not. Long story short, the main idea is if our classifier is trained by the samples in H, it means that our classifier can be trained based on some predefined patterns, and these predefined patterns actually shows the semantics of the app. So it helps our classifier learn these patterns rather than they're relying on some individual features that might be biased. Okay. Actually, in our study, we consider or we did different experiments to measure, to see the performance of all approach. Here, I mentioned some experimental settings. The most important thing is we consider different sorts of malware classifier. For instance, Derby, which is one of the well-known Android malware detection. And also we consider SECAI, which is a secure version of the Derby, and we name our technique Derby Robust. We also consider two realistic evasion attack that works in the different settings. For instance, a problem space, a peak category, which is a problem space, white box evasion attacks. This attack has been proposed in one of the XMP paper in 2020. And also Evaderol, which is a black box problem space evasion attack. We consider different evaluation metric for measuring the performance of all malware detectors. And here I've shown the performance of the malware classifier on the clean data. And as you can see here, the Dragon original has higher clean performance in comparison with the others, but the other robust feature, other defense such as SECAI and also or proposed technique have similar clean performance. And maybe one interesting point is here is the training time of the proposed technique, proposed defense is much more efficient than the SECAI. And also in this slide, I try to show, I reported some results related to adversarial robustness. We consider different sort of robustness, such as transferable robust accuracy and also robust accuracy. I don't want to discuss what is the transferable robust accuracy because in one of the previous talk, one of the guys described this sort of robustness. And as you can see here, for all for both of the type of robust accuracy, our model shows better robust accuracy against Picagreedy and also Ivedroid. And yeah, so I think that it can confirm that our approach makes sense. But we did more analyses. For instance, our analysis shows that using the proposed robust feature space can align malware and adversarial malware distribution better than the initial feature space. For example, here we use the TSME visualization to see how is the distribution of the samples. The subfigure A shows the distribution of the malware and adversarial apps in the initial feature space, and the subfigure B, the right side shows their distribution in our robust feature space. And as you can see, the distribution of the malware apps, and the adversarial malware apps are more aligned in the robust feature space in comparison with the initial feature space. We also figure out that our malware classifier learn the semantic-based features, while the baseline, such as the driving, usually relies on the potential bias in the visual features. For instance, I'm not sure if you can see the picture, the top picture, but in this picture, F1, I've showed the most influential features for both initial feature space and also Windows feature space. F1 is the most influential features for the initial feature space, and as you can see, the most important feature for classification for the Drebin that is trained on the initial feature space is the URL. And I think that you agree with me, we cannot decide about whether an app is the malware or benign or goodware just based on the URL. But our technique, I mean that our robust feature space let the classifier learn better sort of features. For instance, our classifier find that the L1 is one of the most influential features for classification. And as you can see, L1 includes different sort of features such as activities, URLs, services, and providers. And this feature is somehow shows that it's related to the functionality, not just it's not just bias features. And also realistic evasion attacks. The realistic evasion attacks needs more features to bypass the classifier. And this figure, the below figure shows that the realistic evasion attack needs to add more features for achieving success rate. The red curve shows is about our technique, and the other curves are related to the other malware detectors. Okay, now let me wrap up my presentation. In summary, we propose a robust feature space that align the distribution of the malware and adversarial malware to mitigate spurious collisions and consequently improving the adversarial robustness. We evaluated the robustness of our technique and also the baselines against two realistic problem space evasion attacks. We also, all results show that the proposed defense all perform baseline malware detectors. But there is an open question, and the question is whether using a data-driven technique reliable for identifying feature dependency. Because you know that our proposed technique, for us, it's important to identify the feature dependency, and we use the samples in the training set for identifying the dependency. So if you use different data set, you might find different feature dependencies. So it's important to an interesting research section is exploring the distribution sheet or something like this. Thank you very much. I'm happy to take your question now. Thank you very much.
Thanks for the interest. This question where the previous features takes the time to understanding what the features were extracting because I'm extracting. Were extracting the single set of features on the proposed interface. If so, then you spoke about finding out the relationship between the important feature which you want to preserve, right? So if you are using the information from manifest file basically, how do you try to find out the relationship? Because because the manifest file there is no relation because you can just grab the permissions or intent. So how do you try to use graph-based approach to find out the relations?
Yeah, thank you very much. Very nice question. Actually, in the preferred argument, you can build your model with any sort of you can you classify it based on any sort of feature representation. What the idea is, you need to transform your objects from the initial feature space, which can be anything, to another feature representation, another feature space. In order to actually consider grouping feature representations, but we can use any sort of feature representation. And about the second part of the question, the addressing the feature dependencies, that's strong. And we explain the details of the how we identify the feature dependencies. But we use some technique that has been already presented in the literature. For instance, one of the really interesting and nice book is the finding the domain constraint, the feature space of the detection assistant. And I think that one of the outcomes work is the Nicholas Noise, and they provide some arguments about how we can identify the meaningful dependency. For instance, in the paper, they said that we first need to find the primary features and then secondary features, and then using a technique to see which secondary features are related to the primary features. And I just want to say that this is not more contribution. We use for this part, we use the demonstration that has been discussed in the previous.
Thank you.